Okay. Excuse me. We're going to split these notes up into two videos because they're kind of long. This is 6.2 notes, but a different part of it. We're going to talk about other growth models. Now, we already talked about this equation when we were doing exponential growth and decay. Our book refers to that constant as a C. AP sometimes refers to that as Y sub 0. So it's still a constant no matter what. All right. So we got a rate at which the population increases is directly proportional to the square root of the population. Let Y represent the population at any time t, where t is measured in weeks. All right, so we want to write a differential equation. So we're looking at the change in y with respect to t. So that's dy dt equals directly proportional to the square root of the population. So that would be the square root of y. But there could be a constant associated with that. So I'm going to put a k there. All right, so that's our differential equation. Now we want to solve this differential equation. I didn't leave you a lot of room here. So we're going to have to kind of split this in half. All right, so we're going to do the antiderivative. Excuse me. Of dy. And I'm going to bring the y's over to the left, so I'll divide both sides by the square root of y. And then I'm going to kick the dt over to the other side with the constant, so it'll be k dt. I'm going to do antiderivative, both of those. This would be the antiderivative of y to the negative 1/2 dy. I think you know why. Just making it more user-friendly. The derivative, or antiderivative of this would be y to the 1/2 over 1/2. So that would be 2y to the 1/2 equals kt plus some constant. All right. I want to solve this for y, so I'm going to divide everything by 2. That's going to give me y to the 1/2 equals kt over 2 plus a constant divided by 2 is just a different constant, so I'm just going to call that C1. All right. So if I squared both sides of this, I could solve that for y. So I'm going to write that up here. So y would be equal to kt over 2 plus C1 quantity squared. So all I'm doing is squaring this equation, both sides of the equation, just to get rid of the 1/2 power. Okay, now we're given the initial conditions of y0 equals 25. So that's going to help us figure out what that C1 constant is. So if I plugged in 25 in for y and 0 in for t, that would give me C1 squared equals 25. So C1 would be equal to 5. All right. So then my equation really becomes y equals kt over 2 plus 5, quantity squared. All right. Now we want to figure out what this constant is, and we're going to use this other condition that they gave us, y of 5 is equal to 100 to do that. So I'd get 100 equals equals 5k over 2 plus 5 quantity squared. I'm going to take the square root of everything here. So that'll give me 10 here is equal to 5k over 2 plus 5. All right. So do some algebra here, and k should come out to be 2. All right, so our equation then from up above would be y is equal to k, which we just found out to be 2, t over 2 plus 5 quantity squared. Then we cancel those 2's. So it's just y equals t plus 5 quantity squared. All right, so that's our answer to part B. Hopefully you wrote smaller than I did. And we're able to fit that in. All right, so I'm going to erase this here in a second because I got to go to the next part. So if you need to pause it, pause it. Okay, so part C says, what's the size of the population after 15 weeks? So we would just take 15 and plug that in for t. So that'd be 15 plus 5 quantity squared, which is 400 people. All right, that's easy enough. And then when will the population reach 1,000? All right, so we're going to set 1,000 equal to t plus 5 quantity squared, and we'll solve for t. So take the square root of both sides, you get t plus 5 equals the square root of 1,000. And so t would be equal to whatever the square root of 1,000 minus 5 is. And let's say we're going to round that because it makes sense to in this, because we're talking about, I think this is weeks. Yeah, it's measured in weeks. So that should come out to be, so when in doubt, we go 4 decimal places. So 26.6228 weeks. Okay, so that's the first problem. Definitely the hardest part of that is B, where you have to solve the differential equation for those initial conditions to find out what your 2 constants were. All right, let's go on to number 2. Okay, Newton's law of cooling states that the rate at which temperature of an object decreases is proportional to the difference between the temperature of the object T, capital T, and the temperature of its environment, which is constant. All right, so a cup of coffee with an initial temperature of 95 degrees is placed in a room that is 21 degrees Celsius. Write a differential equation that models the above situation. Okay, so we're the rate of change at which the temperature is changing, which is capital T, with respect to time, so little t. So d capital T over dt is equal to the difference between t and its environment, which in this case would be the temperature of the room, which would be 21. So T minus 21, but remember there could be a constant in front of that. Okay, so that's our differential equation. Now we're going to solve this. And just like we did on all the other ones, we got to get the capital T's on one side and the lowercase t's on the other side. All right, so we would have here. So we would get antiderivative of, so I'm going to bring the t minus 21 over to the left, so I have to divide that. So it'd be d capital T over t minus 21. Kick the dt over to the other side, so that would just be k dt. And we're going to do the, oh shoot, we're going to need room on both sides here. Oh, write smaller. So erase that if you need to, because we're going to need lots of room, more than on the last problem. Okay, so we're going to do the antiderivative of the left side, and that's going to be the natural log of the absolute value of t minus 21, which, oh, okay, here's your Easter egg. I like this song. Some of y'all never been down south too much. I'm going to tell you a little bit about this so that you understand what I'm talking about. It's called Swamp Rock. And you need to tell me the time at which this song came on, and you need to get the name of the song and the artist that performs it. And you give me a direct message, and you get extra credit. Might have to Shazam it. I'm going to leave it play for a minute. No, not a minute. They did all right. I'm down in Louisiana, where the alligators grow so mean. There lived a girl that I swear to the world made the alligators look tame. Poke salad Annie, poke salad Annie. Okay, back to calculus. All right, so that's the left side. That would be equal to kt plus a constant on the right side. All right. We need to find out what that c is. We're solving this differential equation given the temperature of the coffee is 85 degrees. All right, so after 1 minute. Oh, I just caught that. Okay, so the initial constant, the initial temperature at time 0 is 95 degrees. All right, so I'm going to use that to find this C right here. And I'll use the 85 after 1 minute to find little k. All right, so we'll go natural log, absolute value of 95 minus 21 equals k times t, which would, our initial time is 0, plus c. Okay, so the natural log of 74, I can drop the absolute value equals c. All right, and I want to find I want to go back to our equation from up here, this equation right here. And I'm going to plug in the natural log of 74 in for that constant right there. All right. Because again, I'm looking to solve this differential equation. So I want t is equal to something. All right, so that'll give me the natural log of t minus 21 equals kt plus the natural log of 74. All right. Okay, then we're going to do e to the, because I want to solve for big T. All right, so that's e to the ln of t minus 21 is just going to be t minus 21. And I can drop the absolute value bars now. This, we're going to do that trick again where if we're doing e to some power, we can split that up into multiplication. So e to the kt times e to the ln 74. All right. Now, this part right here is just a number. It's another constant. So this would be t minus 21 equals e to the kt. And e to the ln of 74 is just 74 by property of exponents. All right. So now we can solve this for t by kicking the 21 over to the other side. And we'll get t is equal to 74 e to the kt plus 21. All right. So that's my solution to my differential equation. All right. Now, like on the last problem, we're going to take that equation. We're going to use the second condition they gave us, which is the coffee temperature is 85 degrees after 1 minute, to find little k. All right, so that should make sense, hopefully. All right, I didn't leave myself enough room, so it's all gotta go. One more time. Okay, so I would then have 85 is equal to 74 e to the k times 1 after 1 minute. All right. Oh, I forgot my plus 21. Okay, so kick the 21 over to the other side. So what's that going to give me? 64 is equal to 74 e to the k. All right, I want to solve this for k, so we want to get that k out of the exponent. So we're going to take the natural log of both sides. I could kick the 74 over by dividing both sides by 74, and it's probably going to be the same amount of work either way, but you can do it now or do it later. Okay, so this is going to be the natural log of 64. This is going to be, since it's multiplication, the natural log of 74 plus the natural log of e to the k. Yeah, actually, now that I think about it, probably would have been smart of me to kick the 74 over to the other side. All right, So we're going to subtract natural log of 74. So the natural log of 64 minus the natural log of 74 equals the natural log of e to the k. And that would, we know that's 1, and we can take that and stick that out front. So that's just k times 1, which is k. Okay, so k then would be equal to the natural log of 64 minus the natural log of 74, which we could rewrite as the natural log of 64 divided by 74 as a single log, because properties of logs. And then that can be reduced to the natural log of 32 over 37. All right, so that's our constant, our k constant. Okay, so now we got to go and write our equation. All right, so somewhere up above, we got t is equal to 74 e to the kt. And k is the natural log of 32 over 37 times t plus 21. Now, to be honest with you, I don't know if they might count off on this if this was an AP problem, which, by the way, so I just got a email from AP that said it looks as of now that people are going to be taking AP exams at home, and in the case of calculus, I don't know about other AP exams, and it's just going to be FRQs, no multiple choice. So that's what's being bantered about now. So we'll see what happens in the future. All right, but if this were FRQ, they might let you get away with that. But e to the ln is one of the properties of exponents. They cancel each other out. So you could really write this as t equals 74 times 32 over 37 t plus 21. All right. Okay, so let's go to hang on a second.